Now there's one other point that is very important on an airfoil, and that is called the aerodynamic center. The aerodynamic center, by definition, is the point where the change in pitching moment with respect to angle of attack is zero. So if we come back up here to our drawing of the airfoils, what happens is as we increase the angle of attack, our pitching moment is going to change because the normal force, for example, is going to increase as long as we're below stall. The axial force will also be changing. And so our forces and moments are very much dependent on our angle of attack. Well, there's a point on this airfoil where, along the x-axis of this airfoil, where as we increase the angle of attack, our pitching moment actually does not change. And so we can find that from, again, by using equation 2 up here. We'll just rewrite that here. So we've got the pitching moment at the leading edge is equal to the pitching moment at some x location minus x over c, c sub n. And then we can write that same equation at our aerodynamic center, so that the pitching moment at the aerodynamic center minus x AC, we're going to put XAC as the location of the aerodynamic center, divided by C, Cn. So I've just rewritten equation 2, but I've included the location of the aerodynamic center. So the definition of the aerodynamic center is the point where the change in the pitching moment with respect to angle of attack is zero. So what we want to do is take the derivative of this whole equation with respect to angle of attack. And so that's pretty simple to write out. We're just going to say the pitching moment at the leading edge with respect to alpha, or the change in that with respect to alpha. Now, I use a comma to represent a derivative. So comma alpha means the change in the pitching moment at the leading edge with respect to alpha. So in fact, I'll just write that out here. So CMLE d alpha. That's what. So I'm going to use shorthand. I'm just going to use a comma there to denote that. So if we continue through on this equation, we're just taking the derivative of everything with respect to alpha. So it's going to be CMX comma alpha minus, now x over c is not dependent on alpha, but the normal force is, so it's going to be Cn comma alpha there. Is equal to, and I can take the derivative of this next guy, which is the aerodynamic center with respect to alpha, the pitching moment at the aerodynamic center with respect to alpha, minus XAC over C times Cn alpha there. Okay, so what we're trying to do is find the aerodynamic center, XAC over C. We're trying to solve for this guy. Now, by definition, that location is the point where the pitching moment with respect to alpha or the change in pitching moment with respect to alpha is zero. So that means that this term is zero. The change in if you look at the pitching moment at the aerodynamic center and look at the change with respect to alpha, that has to be zero by definition. So with that equal to zero, now I can solve for XAC over C in terms of the pitching moment at the leading edge or the pitching moment at another location. So let's look at it in terms of the pitching moment at the leading edge. So XAC over C equals, let's see, it's going to be minus CM leading edge comma alpha divided by Cn alpha. So if I know the information at the leading edge, if I know the derivative of the moment at the leading edge with respect to alpha, and I also know the derivative of the normal force with respect to alpha, I can find the location of the aerodynamic center. Now, if I know that information so we use that to get there. If I know this information at some other location, I can solve for the aerodynamic center. And let's see, that's just going to be x over c minus cmx alpha over cn alpha. Okay, so this is this equation now can be used to find the aerodynamic center if I know the pitching moment at the leading edge or the pitching moment at another location. I can plug it into this equation to find the location of the aerodynamic center. Now, one location that is very common for reporting moment coefficients is at the quarter chord, and we'll find out more why that is once we get into thin airfoil theory. But let's just write this in terms of what if I had the information at the quarter chord, then XAC over C is equal to X over C, which is going to be 0.25 or 1/4 because I know it at the quarter chord, minus CM at the quarter chord, comma alpha over CN alpha. So if you're given the information at the quarter chord, then this is the equation. Really, it's just a special case of that equation there where we've just plugged in the quarter chord. But you could have that information at any location along the chord and still find the aerodynamic center.